Welcome back, students. Today in this session we are going to study about the energy of the Bohr's orbits. This is a very important topic which is going to explain you how the energy of each and every orbit is calculated. So, to first begin with, energy is nothing but it's a combination of potential and kinetic energy. So, what I will be doing is I will be individually finding out the kinetic and the potential energy for you to tell how the total energy really works. So, let me first start with the potential energy. So, potential energy here is nothing but the typical electrostatic potential energy, because at the center of the atom we have a positive charge and the negative charged electron is actually going around that positively charged ion. So, see, ZE is the charge of your nucleus times negative E is the charge of the electron divided by 4 pi epsilon naught into Rn. This is how we represent the potential energy between the nucleus and an electron. Now, what I will be simply doing is I will be rewriting my Rn. What is Rn? Rn is nothing but the radius of the orbit. So, listen, where Rn is equal to n square h square epsilon naught by z pi m into E squared. We already know this particular equation which I have derived in the previous session. Now, I will just take this and I will plug it into this. So, listen, Pe is equal to minus Ze squared divided by 4 pi epsilon naught into n square h squared epsilon naught divided by z pi m into E square. Okay. So, this is how it is written. So, now what I am going to do is I am going to rewrite the whole stuff, where first pi and pi will go down, then Pe is equal to let us see, here we have E square Ze squared, whereas in the Rn we again have E squared. So, that goes up. So, it becomes minus Z squared e power 4 in the numerator divided by 4 n square h square epsilon naught square. So, this is the equation for your potential energy, minus z squared m e power 4 times m, we should not forget that m, divided by 4 epsilon naught square n squared h square. So, this is how we write the expression for the potential energy. Similarly, we are going to express the kinetic energy. Listen, now kinetic energy is Ke of 1 by 2 m into Vn squared. 1 by 2 m into Vn squared. We again know the expression for the velocity, which is nothing but Ze square by 2 nh epsilon naught. Ze squared by 2 nh epsilon naught. So, I will substitute this back into the equation to find the kinetic energy, which is equal to 1 by 2 into m into Ze square by 2 into n into h into epsilon naught the whole squared. So, I will square it and I will put it back into this, where kinetic energy is equal to z squared m e power 4 by 8 n square h squared epsilon naught squared. So, this is the expression for the kinetic energy. See, this is the expression for the potential energy. So, the total energy is nothing but the potential energy plus kinetic energy it is. So, I will add them up. So, what happens is E is equal to, you see, this is the higher term which has a negative sign in it. So, on adding this, we get minus z squared m e power 4 by 8 n square h square epsilon naught squared. This is the expression for the energy. This is the expression for the energy. See, it is very easy and simple again. Again, if you just take a close look at this, except for z and n, rest of the things are constant. So, if I try to evaluate them, En is equal to minus 13.6 into z squared by n square it is. Minus 13.6 z square by n square it is. This is the expression for the energy. What energy? Energy of each and every individual orbit. Okay, in case if you are trying to find the energy for any atom, you have to just substitute the atomic number of that particular atom and the number of the orbit for which you are trying to find the energy. Clear? So, this totally gives you the energy of your Bohr's orbit. So, just for instance, if you are going to try and calculate the energy of an hydrogen atom, okay, so Z for the hydrogen atom is 1, and if I take n is equal to 1, then E1 is equal to minus 13.6 electron volt. That is important. See, I haven't written it like here. Please write it down. This is calculated in terms of electron volt. Okay. So, now we can also rearrange the whole equation to find the Rayberg constant. So, to do that, En is equal to minus z squared m e power 4 by 8 n square h squared epsilon naught squared. Here, what I have to do is I have to simply multiply this with Hc and divide it with Hc, and this whole thing, okay, wait, let me slightly rewrite this so that it will be very handy for us. Yes, En is equal to minus of z squared by n squared, I will split this out, into Hc, I will again split this out, into m e power 4 by 8 n square h cube epsilon naught squared into c. This is what the Rayberg constant is. Rayberg constant. Okay, and the value of the Rayberg constant is 1.03 into 10 power 7 per meter is the value of the Rayberg constant. Okay, so in order to do the calculation, you must be aware of what the Rayberg constant is and what are the expressions that involve inside the Rayberg constant. Okay, remember this z and n will be left untouched, but only if you multiply and divide it with Hc, you get to know how your Rayberg constant looks. This Rayberg constant actually plays a very major role when you go into studying the hydrogen spectrum, which we will be doing it in the next session. Okay, so this is how the energy is totally written. Now, there are various types of other energies that we could also study, where the first one is the ionization energy or potential. Ionization energy. So, what exactly you mean by the ionization energy? It is very simple. The amount of energy that is required to ionize an atom. What do you mean by ionizing? To take an electron from the ground state to the infinite state is called the ionization energy. So, E is equal to E infinity minus E1. E1 is your ground state, E infinity is the energy associated with the energy level that is at the infinite point. So, let me write it one by one. Listen, what is E infinity? E infinity is nothing but 0 minus of minus 13.6 z square by n square. I will assume the whole thing is operating for the hydrogen atom. So, the ionization energy is equal to plus 13.6 electron volt, whereas ionization potential means it is nothing but V is equal to 13.6 electron volt divided by E. This is how it is written, 13.6 electron volt divided by E. This is your ionization potential. So, this is how the whole thing is written in terms of ionization potential and energies. Likewise, there is something else called as the excitation potential or excitation energy. What exactly you mean by the excitation? Excitation energy. Excitation energy is very simple. Amount of energy that is required to excite an atom. For example, excitation means taking it from an initial energy level to the final energy level. So, which is equal to minus 13.6 divided by NF squared, assuming that we are operating with hydrogen atom, Z is equal to 1 minus of 13.6 divided by Ni squared equal to, I can pull this 13.6 outside, it becomes 1 by Ni squared minus 1 by Nf squared it is. So, this is the excitation energy. This is the excitation energy, the energy that is required to take the electron from the initial level to the final level. Clear? In case if I ask for the excitation potential, just simply divide it by E, because the whole thing is in terms of electron volts. In order to get it in terms of potential, you have to divide it with the charge of the electron. It is that simple. So, these are the different energies that are associated with the Bohr's atom, and remember, this particular topic is very important, that you will get many questions out of it. Okay. Apart from this, I would like to add something. E is equal to h mu. Likewise, E is equal to h into C by lambda. Energy and lambda are closely associated. Remember something, we used to find the de Broglie wavelength for an electron. Okay. So, how does an electron has its own wavelength? Only if the electron moves with some particular velocity. If the electron moves with some particular velocity, it has its own wavelength called as de Broglie wavelength. Here, I use this equation to find the energy of the orbit. Only if the energy of the orbit and the energy of the electrons are equal, the electron is allowed to stay inside that orbit. Who decides that? It's it's de Broglie wavelength decides it. You find the de Broglie wavelength of the electron, and if you try to fit that wavelength into this orbit, it should completely satisfy it. This is your de Broglie wavelength. I take the de Broglie wavelength and I bend it, and if I put it like this on an orbit, it should perfectly satisfy. Only then that particular electron is allowed inside an orbit. This is the close relationship between the de Broglie wavelength and the energy of the orbit. In case if this de Broglie wavelength doesn't suit the orbit, then that electron is not allowed inside, which means that electron will have excess energy or lesser energy than the particular orbit. So, it has to either jump to the higher level or it should jump to the lower level to fit itself into that orbit. Okay, that is purely decided based on the de Broglie wavelength. So, the equation is written like this: 2 pi Rn is equal to n lambda. Circumference of the radius, circumference of the orbit is equal to n times the de Broglie wavelength, right. So, this is also a very important information that you should understand as far as the modern physics is concerned. With this note, we come to the end of this session. Again in the next session, we will talk about the hydrogen spectrum. Thank you.